Hello, everyone. It's been quite a bit since I made one of these videos. I kind of didn't make one for a few weeks, and then the holidays happened. You probably know how it is, but it's fine. I'm back, and I'd like to continue the little video series I'd started on the GHC optimization pipeline. So today I want to talk about sort of a more specific optimization than what I talked about last time. Last time we just talked about some of the simplifications, local transformations that the simplifier does. But today I want to talk about sort of two closely related optimization passes in GHC, one of which is the demand analyzer, a significant part of which is the strictness analyzer, and then something known as the worker wrapper transformation, which is one of my very favorite optimizations that GHC does. And as we get into it, you may hopefully see why. So I've just kind of created this simple example of these two very, very small functions. And small functions are good because if we're going to be looking at core, we want things to be small because things tend to get a lot bigger when we transform them from Haskell into core. But one problem of using really small functions is that GHC gets very, very keen to just inline everything. And we don't really want GHC to inline everything because this is specifically an optimization between functions, between function calls. And so if GHC were to inline this function, it wouldn't be able to actually see what we want to see. So I've added this no inline pragma, but of course just know that in a real program, you wouldn't have this here. It would just be, you'd have a bigger function, and so GHC wouldn't just immediately inline it. So anyway, we have these two functions. One of them is just sort of a safe division operation. We have this, we have this case that checks if the denominator is 0. If it is, we return nothing. Otherwise, we actually perform integer division. And then we have this simple function that just wraps it and divides sort of two squares of two different numbers. And I want to take a look at what core GHC generates, but specifically, I'm going to run this big long command. Unfortunately, it's a little hard to see, but most of these flags here are just printing things out. Specifically, what I want to call attention to is that I'm going to compile with optimizations, but I'm going to pass this flag, which I would normally never pass, and there's almost no reason to pass it unless you're doing what I'm doing right now, but I'm going to disable the worker wrapper transformation pass. So I'm going to be running all the optimizations except for this one, so we can kind of see what goes wrong and what problems that causes. So if we take a look at the core that gets generated, as you can see, it is in fact quite a bit larger. There's a few things that I want to call your attention to, and the most significant one is that ints in Haskell, the int type is boxed. It is represented as a pointer, and that pointer is to some heap allocated thing that contains a machine integer inside of it. And so it's actually just defined as an ordinary algebraic data type. It looks kind of like this. So it's just an ordinary algebraic data type that wraps this unboxed int hash type, and we have this constructor with a funny name called ihash, but it's really just an ordinary data constructor. And so int hash is magical. It's primitive. It's built in, but the int type is not. And so whenever we actually want to do some arithmetic, like here is where we're actually calling this div int primitive, div int hash, all of the arithmetic primitives themselves operate on these unboxed int hash values. So in order to actually do anything, we need to first unwrap the integers. So in this case, you can see we're pattern matching on them, just like any other data type. And we're pulling out the unboxed integer inside and then doing some arithmetic. And in particular, this has sort of implications for this div squares function, because as you can see, what we have to do is we have to first pattern match on each of the arguments. I don't really know why GHC is doing one of these pattern matches outside the call and one of them inside the argument, but it's fine. We do these two pattern matches, and then what we're going to do is we're going to do the arithmetic, but then we rebox the value. So when we actually apply this constructor here, we're going to be creating a new heap allocated int value. And I think this is particularly easy to see if we look at actually the generated STG, which is sort of one layer lower than core. But the reason for that is that STG represents all heap allocations using a let. So wherever we see let, we know that that corresponds to a heap allocation. And when we have just case expressions, that's not doing any allocation. So we can see that in this div squares function, we do two heap allocations, one for each argument to safe div, and that's pretty bad because, again, this is just a function on ints, not even on integer, on int. These are machine integers, and so we really should not be doing heap allocation in that function. So somehow what we have to do is GHC has to figure out some way to unbox these integers across the call site. And there's a few different ways that different compilers can sort of try to do that. Maybe, they have some specialized calling conventions that certain functions have that allow them to short circuit this process. But GHC has sort of an additional challenge, which is that in GHC things are lazy. And we can't just eagerly unbox everything, because if we were to do that, then that could cause, in order to, unbox something, we have to force it. It can't be a thunk. We have to actually evaluate it. And so we can only evaluate things, or we can only unbox things if we know that they're used strictly. So what GHC does is it performs strictness analysis of the program to try and figure out which arguments to functions are strict and which ones are lazy. So of course the question then is, how does GHC know whether or not something is used strictly or used lazily? And the answer to that question is it has a strictness analyzer, or actually in its full modern generality known as a demand analyzer. It keeps track of both which arguments to functions are used strictly and lazily, and it also keeps track on which arguments are used at all, which ones are not, and even some information about how many times they're used. And all this information is then used in other parts of the optimizer to make various decisions. So for this particular function, this is the strictness signature, and the syntax here is a little bit, it's very concise. It takes a little bit of time to get used to, but it is actually documented in the GHC user's guide, and there's a section on strictness. And I'm going to break it down and at least focus on the parts that are relevant here. So we have two arguments. Each argument is contained inside of these angle brackets. And for our first argument, it says that it is used at most once. So it might be used 0 times, it might be used 1 time. And that kind of makes sense if we look at our original function, because in this first case here, it isn't used, and in the second case, it is used. Now, that's a little bit misleading, because what the strictness signature is really about is the desugared version, the optimized desugared version of the function. So the fact that we have two cases here and one of them is not used, that doesn't really matter as much as the control flow here. So if we actually look at the body of the function, we can see that here is our first argument, and you can see that we don't actually pattern match on it in every case, because if it turns out that the second argument here is 0, we just return nothing. So this argument is actually not used strictly. It's used lazily, because it might not be evaluated from GHC's perspective. So it's a conservative analysis. If something's used strictly, then it's always used strictly. And this second argument here, on the other hand, has a 1, which means that not only is it used strictly, it's always used exactly once. And so we can see that by looking at this second argument here. We pattern match on it right here, and that's the only use. And then we kind of use the thing inside of it, but we don't use the original value ever again. Now, GHC does include some additional information inside of the strictness signatures here, because from GHC's perspective, int is a product type. We might not think of it as a product type, it only contains one field, but basically as long as there is only one case, then GHC sees it as a product type. And so these things in parentheses are demand information, demand signatures about the things inside of the product. Now, this is a little misleading here, because the demand information for unboxed values is not super meaningful, because unboxed values are always fully evaluated. They can't be thunks. An unboxed integer is just a machine integer. So in this case, it says that it's lazy and lazy, but in fact, that's not entirely accurate. So we'll just kind of ignore that for the moment. But the important thing here is that this first argument is used lazily, and this second argument is used strictly. So GHC knows that this is the case, and what can it do with that information? Well, what it could do is it could generate some kind of, it could use this information to generate some kind of, I don't know, clever jump into the middle of the function. We could pull out the function into a separate function here, this little body, and have that just kind of take two unbox integers, and then in some situations we could then use this strictness information to actually be able to do the unboxing a little more aggressively. Of course, we are doing the unboxing here regardless, because we have to be able to. But, there's some complicated thing that GHC could do, but it's not immediately obvious how we would take advantage of this information. And this is where I think GHC's solution is so cool, because it's a remarkably elegant and simple solution. So I guess first what I'll do is I will show what core gets generated if we compile this module with optimizations enabled and with the worker wrapper transformation enabled. And if we look at this code, we right away can see that we've gotten something significantly different. Instead of having a call in div squares to our safediv function directly, we have a call now to this new function with kind of a funny name, which starts with this $W. And that function is defined up here, and this is known as the worker for safediv. And you can see that now that second argument that was accepted strictly has now been unboxed. And in fact, now, if we look at the STG, we now only have one let. Now, it's important to note that our safe div function is still here. This is what's known as now the wrapper in the worker wrapper transformation. And it's known as the wrapper because it literally just wraps the worker. It just basically accepts two unboxed integers, and then it calls the worker passing the unboxed version of the second argument. And of course, this doesn't change the strictness properties of the program because we knew originally that this function uses its second argument strictly. So we can just pull it out kind of right at the start of the function, pass it to our safe div worker, and everything will still behave exactly the same way. But here's the key idea. The sort of key idea of this whole process is that this wrapper now is very, very small. And the worker itself, because it's basically the body of the original function, could just be arbitrarily large, right? It could be some really big function, but it doesn't matter. The wrapper is still going to be tiny. And what that means is that we can inline it. And so what's happened is we've had this call in div squares to our sort of safe div wrapper, and it's been inlined here. Now, this is where it becomes a little bit difficult to see exactly what's happened to end up with this result because we're just looking at the output of the optimizer. But essentially what's happening is that inside of div squares, if you remember, what we were doing was we actually had something that looks quite a bit like this, right? Where we're, let me just bring this in here. So we were pattern matching on Y, and then we had a sort of unboxed version of Y. And then we are squaring that unboxed version of Y. And then we are going to be taking that and boxing it back up. And so then we pass that to our safe div function. But after so I guess I can just make this a little bit clearer. So we have some expression, we functionally had something like this. And of course, each of these are in parentheses. So what happens after we inline our safe div wrapper? Well, what happens is it turns into something that looks pretty much identical, but we are going to extract the sort of second argument a little bit, immediately, because that's the whole point here. So what we're doing is we're turning this into a use of worker safe div, but we're taking this second argument here. We're going to pull this out into something that does case analysis right at the start. And then this is going to then return some unboxed version of this argument. And we end up with something like this. I think that's right. Yeah, we take this, we unbox it, and then we pass it in as the second argument here. Now, you'll notice that if you watch the previous video I made on the simplifier, this is now a case expression that is scrutinizing the result of a case expression. And so we can do that local simplification, the case of case transformation, which is basically going to take this body here and push it inside of here. So we're going to, and also I'm realizing I'm forgetting a constructor here. There we go. So yeah, so we're going to take this and we're going to push this whole body into here. We're basically going to be turning the case expressions inside out. So we're going to do case analysis on this now. We're going to have this as the body. And I need to remove this outer case. And my parentheses are probably a little bit wrong here, but this seems to be right. So let me rearrange this slightly. There we go. So we're doing case analysis on Y, then we are boxing it up. We're boxing up the result of this multiplication, but then we're immediately doing case analysis. So because we're boxing it and then immediately unboxing it, now we can just completely eliminate the unboxing and reboxing. And we can just take this value here and we can replace this Y prime prime in here and get rid of the entire case. And now we have this expression, which just directly unwraps Y, does the multiplication, and doesn't ever rebox it. We just pass it into this worker directly. And so we've done exactly what we want. We've managed to unbox this function, but we didn't really do anything special to do the unboxing. All we did was mechanically took the body of this function, moved it into another function, and then left this wrapper behind that inlines, and then the ordinary simplifier does the rest of the work. And I think that that is just really, really cool. It's a really clever but really effective optimization technique. And one of the really neat things about it is that it even works across modules, because these functions, these wrapper functions, are so small that GHC just sort of stores their unfolding, their right-hand sides, in the interface file. But it doesn't have to store the entire, worker function there because it's some big function. That can just be in the binary. But it stores this little wrapper, this little kind of stub, and those get inlined across modules, and that means that we get cross-module unboxing basically for free just by taking advantage of the inliner and the simplifier. But of course, knowing which of these arguments to unbox, basically knowing which worker to generate, relies very, very heavily on this strictness signature, and so that's why that's so important. Now, looking at this, we might realize that we're sort of doing something a little bit silly, because we are, in fact, reboxing this first argument here, this first argument x. And so based on everything that we know that really the way to fix that problem, if we wanted to fix that problem, would be to just make it so that this first argument is unconditionally evaluated. So what we could do is we could just add a bang on it here. And then if we recompile, then we will find that indeed we've magically ended up with the first argument being unboxed, because if we look at the strictness signature of safe div, it's now always strictly using its first argument exactly once. And so indeed, if we look at the STG, you can see that we have no lets and no allocation, which is exactly what we want. Now, this I think makes it seem a little bit subtler than it actually is. I think in practice, there are some tricky things to get right with respect to strictness in kind of the core libraries with numeric stuff, but in practice, you don't really have to be worrying quite as much about whether or not particular arguments are strictly used. But it is useful to be aware of, and it does kind of drive this unboxing optimization. So this is kind of the simplest form, I think, of the worker wrapper transformation. And I now want to take a look at a sort of slightly I guess not more complicated, but different way that the worker transformation is applied. So here I have another module with a somewhat different example. And in this particular example, I have a simple little record type here, which defines a user type, and user has a name. We store whether or not the user is an admin, and then they have some age in years. And we have some function to determine whether or not they're a privileged user. And maybe we're a very exceptionally senior respecting sysadmin, and we decide to just make anyone who's above the age of 60 super users. This is not a video about network security. So we have this little function that just checks if they are an admin or if their age is greater than or equal to 60. And again, just as before, I just have this no inline pragma to illustrate the example without GHC, just inlining everything. And then we just have some get display name function. This is just kind of a silly example, but we say maybe we're just going to prefix everyone who's a privileged user with a plus on their username. Just a simple example. So what does this actually generate? Well, if we take a look at the code that gets generated, and once again, I'm going to pass the no worker wrapper option. And we take a look at the results. What we have here is, well, there's a bunch of junk that gets generated at the start for the record selectors. But we have our, somewhere in here, our is privileged function, and we have something kind of interesting in the demand signature, which we didn't have before, which is that now, because it's a record type, it's a product type of 3 fields, and the first one has an A here, and that A stands for absent, which means that it's never actually used in the body. And you can see that this particular argument here is in fact not used anywhere. We use the second argument here, we use the second argument, or the third field here, but this one is never actually used. And so when we then call get display name, what we're doing is we are going to, well, we're passing this entire record structure, even though it really only needs, 2 of the fields. And in general, this, you might have some big record, and it might actually be beneficial to, rather than just passing around some big record, to just pass around the couple fields that the code needs. So once again, the worker wrapper transformation can help with this. So if we go back in here and remove this no worker wrapper flag, then you can see now that we have in fact generated a worker for this is privileged function, and you will note that it only takes 2 arguments. So there's basically 2 things going on here. One of them is that we've unpacked the product. And in general, that might actually be a nice thing to do, because it might be the case that if, for example, we have a function that takes a tuple, but in practice, we have some call site that just kind of constructs the tuple and then immediately passes it, and then the code just unwraps the tuple, then just kind of removing that layer of wrapping is itself a win. So that could be useful here. But what is particularly useful in this example is this fact that we are now dropping one of the arguments. And you can see that in our isPrivileged function here, the wrapper function, then we're just pattern matching on the value. We're pulling out the fields, and these have very unhelpful names, but you can see that we're taking the second one and the third one and passing it to the worker. And so then if we scroll down a little bit and take a look at the getDisplayName function, then you can see that in fact we are calling this, we're now doing the pattern matching a little bit. And so you can see that in the body of getDisplayName, we are in fact only passing these 2 arguments in, and this first one is only used here. So you don't have to continue passing around this whole user value. And in fact, technically the user value itself, if this is the only reference to it, it could be garbage collected as soon as control enters the body of this case, because it's no longer used anywhere. Now, this might not seem particularly significant. After all, you're passing more arguments. Of course, passing a few arguments is basically free. We have a handful of registers to work with, and so those are just going to get passed directly on in registers. They don't even have to be passed on the stack or anything like that. So that's quite nice. But it might not immediately seem like this is a particularly huge win, but there is something that I think comes up quite a bit with both the unpacking of product types and sort of constraining the set of fields that actually get passed down, and that has to do with type classes. So I've now written this final example here, which is just a kind of boring function, also with the no inline pragma, that just operates on some arbitrary type implementing num. And what it's going to do is just a simple multiply add. So we're going to multiply 2 numbers and then add a third number together. So let's take a look first without the worker wrapper transformation at the code that gets generated for this. And it's pretty simple. And I guess I haven't really talked about how type classes actually get compiled, but essentially every type class is actually at the core level just a big record type with all of its methods. And so we're getting passed in instead of, when we have this constraint, this becomes at the core level a real argument, which passes in just a record known as a dictionary of all of the methods of num. And then the sort of plus and multiply operations are just record selectors on that dictionary. So we're just going to be pulling them out. But of course, num has a whole bunch of methods, and we only need these 2. So if we go back into here and enable the worker wrapper transformation, then you'll see that indeed we end up with a worker and a wrapper. And the worker is now, it's again kind of hard to see because the names are super unhelpful. And this just looks like complete gunk. But if we look at the wrapper, then you can see that we're opening up this num dictionary, and we are taking this argument and this argument. Again, the names are very unhelpful, but it turns out that these 2 are the only ones that are used. This is the plus operation. This is the multiplication. They are passed directly to multiply add. And so again, just as with, this, again, it should be noted that this does not, this alone is not helpful, right? If we are just going to be sort of unpacking it and then passing it in here, if this were to get called, then we would just be doing the unpacking in a slightly different place. So it wouldn't be a significant difference. But the whole idea is that as with our module B here, then this wrapper can get inlined. And because of the fact that this gets inlined and one of these fields is never actually used, and we have this like pattern matching here, then the simplifier can clean all that stuff up, and it basically allows us to avoid having to repack and put things back into a record and then pull them out again. And it turns out to be quite a nice win. Now, all of these things that the worker wrapper transformation does can actually be combined. So you can have something that, and I guess maybe I should have come up with an example that does this. Oh, actually, I bet, now that I think about it, I can illustrate this. So if we take a look at our isPrivileged function here, the worker here, then int is not being unboxed. And why is int not being unboxed? Well, if we take a look at the strictness signature here, we can see that the age, I guess, yeah, age is the third field, is used lazily. So it's used at most once, but not necessarily used strictly. And again, if we really wanted to, I mean, I guess one thing we could do is we could flip the order of these around. And if we were to do that, then recompile, then we should see that indeed our worker is now in fact unboxing the int value. And so these things can all be combined, and you can have unboxing and this sort of product unwrapping, and which, I mean, I guess is sort of a form of unboxing as well. And then also the domain analysis, removing certain arguments, and all these things work together very, very nicely. Now, I feel like some of these examples probably give the impression that getting good performance and taking advantage of this is extremely delicate, because like flipping the order of this Boolean operation changes whether or not the unboxing happens, and to some extent that's true. If you are using lazy data types, then small changes to the program like this can have some influence on the strictness information. But I find that in a lot of real Haskell applications that I've worked on, it's a really nice kind of middle ground to enable strict data, so that all of the record fields are strict in each of your records. And in fact, this is getting a little bit further than I intended to go, so I won't go into this in too much detail. But if we do in fact strictify everything here, then what GHC will do is almost certainly unpack this integer directly into this constructor. So rather than even storing a boxed integer, it will store an unboxed integer. And we should be able to see that in the code itself. So first of all, if we take a look at the worker wrapper transformation, you can in fact see that even though I've reordered this back to how it was before, it still is unboxing its second argument. And when we look at the getDisplayName function, it's a little bit hard to see because GHC is not going to annotate the individual types here. But if we look at this isPrivileged function, then it's not doing anything to the second argument, it's just passing it through directly. So indeed, it's being stored unboxed in this data type. So that's not directly related to worker wrapper, but it's another form of sort of unboxing that GHC does, so it's still relevant. So basically, if you use strict data, then I find that in practice, that just kind of generally improves the way that the strictness analyzer runs. It usually is not that much of a benefit to have laziness in your data types. Now, I think some people have a reaction to this, which is that, oh, laziness is just a huge mistake and it's terrible. And, you know, like the situations where it's relevant are not very common. And so I think actually in the next video, I'm going to try and address some of the reasons that I think laziness is not as bad as people think. And it has some advantages that people I think is not always immediately apparent. But for now, I'm just going to say that when everything's working well, when you write Haskell code in this style that is just kind of straightforward, doesn't have too much crazy indirection, so that the strictness analyzer works very, very well, and you use strict data types, then you get very, very nice unboxing, and GHC is able to do very good things to your program. Now, there is one thing that I'm not going to give an example for because this is already getting kind of long, but there's actually also an optimization that GHC does that's very similar, which is called constructed product result, which is where it can actually do similar sorts of optimizations in the result. So if you build up a product type, record type, or a tuple or whatever, and then return it, then GHC can also use that in the worker wrapper to return like an unboxed tuple instead of a boxed tuple, which I think is really neat. So that's all I have to say for this particular video. If you found it helpful, certainly let me know. If you have any questions, let me know. Maybe I can answer them in the future. And hopefully I will see you in the next one, which again, hopefully should not be quite so long this time, but we'll see. See you around.